Today we will discuss third law of thermodynamics. It is very important law because it talks about the entropies at absolute 0. At T equal to 0 Kelvin, the thermal motion of all pure crystals is quenched. That means there is an absence of thermal motion and spatial disorder. This suggests that the entropy of perfectly crystalline substances at absolute 0 should be 0. And this also coincides with the statistical definition of entropy, S is equal to K log W, that if there is only one arrangement in which the crystal can be arranged at absolute 0, W is equal to 1. So, S is equal to K log 1 equal to 0. So, is it that all the substances have entropy at absolute 0 equal to 0 or not? We will further discuss here in this lecture. Let us look at the formal definition of third law of thermodynamics. It states that if the entropy of every element in its most stable state at T equal to 0 is taken as 0, then every substance has a positive entropy which at T equal to 0 may become 0 and which does become 0 for all perfect crystalline substances including compounds. And the entropies which are based upon S 0 equal to 0 are called third law entropies, or we just often call them entropies. Now, you see, by this definition we say that at absolute 0 all perfectly crystalline substances including compounds have entropy equal to 0. In fact, the third law does not say that the entropy of all perfectly crystalline substances is equal to 0 at absolute 0. It should be interpreted in this way, that the extent of order in all perfectly crystalline substances at absolute 0 is same, and by taking this value equal to 0 is just a matter of convenience. That is why for all the perfectly crystalline substances we set S 0 equal to 0, and in the previous lecture you remember that we discussed how to get the temperature dependence of entropies, and we also discussed that the entropy at any temperature can be calculated if we have the information on the value of S 0. And if we set S 0 is equal to 0, then the entropies based upon this are called third law entropies. How do we get standard reaction entropies? Standard reaction entropies can be calculated from this expression, that is delta S naught. This R subscript signifies reaction. Sometimes many books write R, many books do not write R, so do not get confused. The reaction entropies or change in entropy during a reaction can be calculated from this expression summation j nu j S m naught j, where j is the species j and nu j is the stoichiometric coefficient. How to interpret this? What we just discussed, that the reaction entropies is equal to summation j nu j Sm naught of species J. Suppose my reaction is A moles of A are reacting with B moles of B and producing C moles of C, then according to this equation, delta R S naught will be equal to, I expand this stoichiometric coefficient is positive for products and negative for reactants. So, C is a product, which is therefore, it will be positive, that means C times molar entropy of C, and now I will use negative for the reactant, minus A times molar entropy of A minus B times molar entropy of B. This is how to interpret this. So, this is how to expand this summation. Now, let us discuss the technological applications of entropy. There are several technological applications of entropy and several applications of the information that is coming out from the change in entropy, but let us discuss first of all one example. Let me ask a question first. What is the value of the world record lower temperature ever achieved by anyone? The answer is that scientists have been able to achieve temperature as low as of the order of picokelvin. Picokelvin means 10 raised to the power minus 12 Kelvin. How does one achieve? Entropy has a large role to play here. So, let us discuss how to achieve this low temperature. Gases can be cooled by Joule-Thomson expansion below their inversion temperature, that we know. Helium can be used, the boiling point of helium is 4 Kelvin. Therefore, by evaporating helium, one can easily achieve temperature down to 4 Kelvin. Now, if you evaporate helium by pumping through large diameter pipes, then helium will absorb energy from the pipes, whatever material is used, and it will produce cooling. Temperature down to 1 Kelvin can be produced by this method, by evaporating helium through or by pumping helium through large diameter pipes. Below this temperature, that is below 1 Kelvin, the volatility of helium is very low and its superfluid phase begins to interfere with the cooling process, and therefore, you cannot achieve a temperature below 1 Kelvin by pumping helium through large diameter pipes. Therefore, what method is used? The method which is used to achieve very low temperature is called adiabatic demagnetization process. Let us discuss what is adiabatic demagnetization process. We just discussed that every substance has a positive entropy. The entropy surely will depend upon the temperature, because if the temperature is increased, the extent of disorder will also increase. So, usually when the temperature is increased, the entropy also increases. Let us take a look at a blue line in this figure. As the temperature increases, so this is a plot of entropy versus temperature. So, with increase in temperature, the entropy is increasing in a non-linear fashion. So, what is done is, a substance which has large number of unpaired electrons, which is also called a paramagnetic substance, is taken. The example of such a substance is gadolinium sulphate octahydrate, or one can usually take sample which is paramagnetic material, usually will be from D or F block metal complex, and we just discussed that how to achieve a temperature of about 1 Kelvin. So, let us say we take this sample like gadolinium sulphate octahydrate and plot its entropy against temperature. This is the behavior, this is the variation. And there are large number of unpaired electrons, so paramagnetic substance. When this substance is subjected to magnetic field, what is the effect of magnetic field on paramagnetic substances? More electrons will align in the direction of the magnetic field. So, if by the application of magnetic field more electrons get aligned along the field, more alignment means what? More alignment means the order is increasing. If the order increases, the entropy decreases. So, that means for a magnetized sample, this will be the behavior of entropy, the red line. The entropy is lower than the unmagnetized sample at any point. This curve is for a unmagnetized sample, and this curve is for a magnetized sample. So, what is done is, the substance is cooled to about 1 Kelvin. Let us say we start with the point A, from the point A, and then let the substance be surrounded by helium gas, which will act as a thermal contact between the sample and the cold sink. Under isothermal conditions, turn on the magnetic field. Isothermal condition means the temperature has to be constant. You see here, the temperature should remain constant, and when you turn on the magnetic field, the corresponding point on the magnetized curve, or the curve corresponding to magnetized sample is B. Initially, the entropy was corresponding to point A. When the magnetic field is turned on, the entropy decreases, and the corresponding point on the magnetized sample entropy temperature curve is B, and this vertical line means temperature is remaining constant, and then temperature is kept constant by means of having helium gas surrounding the sample, which I just said is acting as a thermal contact with the cold reservoir. The second step, B to C, means you turn off the magnetic field very slowly in a reversible manner. I repeat, switch off the magnetic field very slowly in a reversible manner under adiabatic conditions. That is what is called adiabatic demagnetization. You recall the Clausius inequality ds is greater than or equal to dq by t. Now, if I under adiabatic demagnetization, if the process is reversible, then I will have to use equal to sign. It is dq reversible by t, process is reversible. And since the process is adiabatic, the value of dq is equal to 0. That means, the entropy of the system should not change. There is no change in entropy of the system. So, if there is no change in entropy, then it should be horizontal here. The dependence should be horizontal. B C corresponds to no change in entropy. The corresponding point now on the unmagnetized sample curve is C. A to B was isothermal magnetization process and B to C is reversible adiabatic demagnetization process, and since there is no entropy change, the path followed will be from B to C. Now, if you carefully examine what has happened from B to C, it has led to cooling. The temperature has changed towards lower temperature. So, you see this one cycle of A to B and B to C has led to lowering of the temperature, and if we repeat these cycles, we will keep on moving towards lower and lower temperature. This is how the adiabatic demagnetization process is used to achieve low temperature. Remember that the kind of temperature, low temperature that I talked about, the picokelvin, is actually achieved by using the nuclear magnetic moments rather than the electronic magnetic moments. So, that is why the comment mentioned here is that even lower temperature can be obtained if nuclear magnetic moments are used, that is process then will be called adiabatic nuclear demagnetization process. That is, instead of the using the magnetic moments of electrons, we use that of the nuclear. So, a natural question that can arise from this discussion, let us again look at this figure, that if we repeat this kind of A to B, B to C kind of processes, we will keep on going towards lower and lower temperature. Will we be ever able to achieve 0 Kelvin by repeating this isothermal magnetization and then followed by adiabatic demagnetization process? Let us take a look at. First, let us take a look at the figure on the left hand side. According to this figure, you see the cycles isothermal magnetization, adiabatic demagnetization, isothermal magnetization, adiabatic demagnetization. Yes, we should be able to achieve absolute 0 provided the temperature, entropy versus temperature curves are like this, which do not coincide at absolute 0, but this is a violation of the third law of thermodynamics. The third law of thermodynamics says that for the pure crystalline substances, we should get coinciding entropy temperature curve at absolute 0. In such a case, you can never achieve absolute 0 in a finite number of steps, and this is formulated in the form of another law, this is formulated in the form of an alternate form of third law, which says that it is impossible to reach absolute 0 in a finite number of steps. In other words, we can say that no one has ever succeeded in cooling any system to absolute zero. So, the third law can be expressed in terms of entropies, that entropy at absolute zero is equal to 0, as we just discussed for perfectly crystalline substances. And an alternate form, this which is also sometimes used, that it is impossible to reach absolute zero in a finite number of steps. So, we have now discussed a lot about the entropy. We discussed that the criteria of spontaneity in terms of second law of thermodynamics is that the entropy change in the system plus entropy change in the surrounding should be greater than 0. So, if we strictly follow the second law to understand the spontaneity of a process, we will have to calculate the entropy change in the system, we will have to calculate the entropy change in the surrounding, add up the two and then see the outcome. But can we derive criteria of spontaneity in terms of properties of system alone, where we do not have to worry about calculations in the surroundings? Surroundings will be connected or will be inbuilt in our calculations anyway, but let us discuss the criteria of spontaneity in terms of properties of system alone, and at the same time we will also defend those criteria of spontaneity in terms of the second law of thermodynamics also, and prove that yes, those criteria of spontaneity also obey the second law of thermodynamics. Let us move towards that. We will derive criteria of spontaneity in terms of entropy alone, entropy of the system alone. We will not worry about entropy of the surrounding. We will also derive in terms of internal energy, enthalpy. Let me introduce another term, it is called Helmholtz energy, defined by or designated by the symbol A, letter A. This is equal to U minus T s, and the Gibbs energy G. This is the symbol used or letter used for Gibbs energy, G is equal to H minus T s. Many times we ask this question that can you define Helmholtz energy? How do you define Gibbs free energy? There should be no confusion in the definition. The definitions of Helmholtz energy or Gibbs energy are simply, for Helmholtz energy, A is equal to U minus T s and G is equal to H minus T s. U, T, S are all the thermodynamic properties of the system. G, H, T, S are all the thermodynamic properties of the system, right. So, therefore, if someone asks that can we define Gibbs free energy or Gibbs energy, the answer should be G is equal to H minus T s. Now, let us derive the criteria of spontaneity. It is very easy. I will start by the Clausius inequality, which says that ds is greater than or equal to dq by t. Let me rewrite this in this form, Tds is greater than or equal to dq. If I keep the volume constant, then you know that heat supplied at constant volume is equal to du. We have discussed it earlier. Now, this inequality gives rise to two criteria of spontaneity. The first criteria of spontaneity will be ds at constant u and v will be greater than or equal to 0. If you fix internal energy, du is equal to 0, right, constant u, and constant v. If I fix u and v, then ds should be greater than or equal to 0. The second criteria of spontaneity is du. Now, I fix the entropy. If I fix the entropy, ds will be 0. So, entropy and volume anyway we have held constant should be less than or equal to 0. You see, we have derived two criteria of spontaneity from here. One is ds at constant u and v should be greater than or equal to 0, and the second one is du at constant s and v should be less than or equal to 0. Please note that here we are only talking about the system, we have nowhere talked about the surroundings. That is why we call these as the criteria of spontaneity in terms of the properties of system alone. But any criteria has to also obey the second law of thermodynamics. Do these derived criteria obey the second law of thermodynamics? Let us see. Let us now take a look at this criteria of spontaneity. According to this criteria of spontaneity, you fix the internal energy, you fix the volume, the entropy of the system must increase during a spontaneous process. See, equal to sign is applicable for reversible process, and if the process is spontaneous, we use greater than sign. So, according to this, the entropy of the system must increase during a spontaneous process, which is actually the content of the second law of thermodynamics. So, it does obey the second law of thermodynamics. On the other hand, for this criteria of spontaneity, according to this, if the entropy of the system is held fixed and the volume is held fixed, then the internal energy of the system must decrease. I repeat, if the entropy is held fixed, then the internal energy of the system must decrease. According to this criteria, if delta S system is 0, if the entropy of the system is held fixed, means delta S for the system is 0, then according to second law, the delta S of surrounding must increase. And that is what is seen in this criteria of spontaneity. The decrease in internal energy will enter the surrounding in the form of heat and will generate more disorder in the surrounding. So, this criteria of spontaneity is to be viewed as the entropy of the system is remaining constant. Therefore, for the process to be spontaneous, the entropy of the surrounding must increase. How it will increase? Some of the internal energy must decrease in the form of heat to enter the surrounding and hence generate some disorder there. So, you see that although we are writing these criteria of spontaneity in terms of properties of system alone, it is automatically connected with the surrounding, and these criteria of spontaneity are obeying the second law of thermodynamics. Let us derive few more criteria of spontaneity. Once again, I start with the same definition, ds is greater than or equal to dq by t, and Tds is greater than or equal to dH. Here I will put the pressure constant, because dq at constant pressure is equal to dH. And here the criteria of spontaneity will be ds at constant h and p should be greater than or equal to 0, and dH at constant s and p should be less than or equal to 0 by the same arguments that we discussed earlier. And the interpretation is also similar, that here according to this criteria, if you fix the enthalpy, the entropy of the system must increase, that is the content of the second law. And here in the second criteria here, if I fix entropy, some of the enthalpy must decrease, the enthalpy of the system must decrease and enter the surrounding in the form of heat to generate enough disorder, so that delta S system plus delta S surrounding is positive. So, this is criteria number 3, this is criteria number 4. We will derive 2 more criteria of spontaneity. First, let us talk in terms of A. A is equal to U minus Ts. A is Helmholtz function or Helmholtz free energy. U is internal energy, T and S have their other usual meanings. Let there be some advancement. So, dA is equal to du minus Tds minus STT. Rewriting this, dA is equal to du minus Tds at constant temperature. And we have earlier derived, you remember that we talked about that Tds is greater than or equal to du at constant volume. We have already discussed this. Now, if I combine these two, du minus Tds should be less than or equal to 0 at constant volume. Once again, du minus Tds should be less than or equal to 0 at constant volume, which if I substitute in this, I get dA at constant temperature and volume should be less than or equal to 0. This is another criteria of spontaneity. That is, for a process which is carried out at constant temperature and fixed volume, the Helmholtz free energy must decrease. Is it a very useful criteria of spontaneity to be used for processes? It is one of the criteria, but the difficulty in this is that this will only be applicable if the volume is held constant. Let us now discuss the most widely used criteria of spontaneity in chemistry, and that is in terms of the Gibbs free energy. G is equal to H minus Ts. So, dG is equal to dH minus Tds minus SDT. Now, I can write dG is equal to dH minus Tds at constant temperature. And by our earlier discussion, Tds is greater than or equal to dH at constant pressure. So, from this dH minus TdS at constant pressure should be less than or equal to 0. I combine the two and come up with this criteria of spontaneity: dG at constant temperature and pressure should be less than or equal to 0. This criteria of spontaneity is most widely used criteria of spontaneity in chemistry or chemical engineering or wherever we want to use the definition of G in defining the criteria of spontaneity. See, most of the time we say a process is spontaneous if delta G is negative. And this criteria of spontaneity is exactly the same, that for a finite process delta G should be negative for a spontaneous process. But we should also assign these constraints when we are talking that delta G is negative. Delta G is negative under constant temperature and pressure conditions. This is how we define the criteria of spontaneity. So, the criteria of spontaneity in terms of properties of system alone, there are 6 criteria of spontaneity in terms of entropy, internal energy, enthalpy, Helmholtz free energy or Gibbs free energy, and this one dG at constant temperature and pressure is less than or equal to 0 is the most widely used criteria of spontaneity, because it is very easy to carry out the processes at constant pressure rather than fixing the volume. And we also discussed that all these criteria of spontaneity, which are defined in terms of properties of system only, also obey the second law of thermodynamics. So far we have discussed a lot about entropy, and as we will see later on that the changes in entropy provide a lot of information, and the second law of thermodynamics is obeyed in all conditions. Today we also discuss the criteria of spontaneity, which will be very useful in predicting whether the process will be feasible at a given condition or not. Thank you very much.